As I've mentioned before, the fork-join pool in general and the common fork-join pool in particular are very powerful, very interesting abstractions. This class doesn't go into much depth on those. The other class will, but I don't want to leave the topic without giving you at least a bit more understanding of what's going on under the hood, because it's really important to at least have a fairly good knowledge of this, if for no other reason it's really cool. So we're going to talk about how parallel streams and that abstraction maps onto the common fork-join pool. And we're actually going to take a look at some of the source code from the streams framework, and I will explain to you the relevant parts of it. So the way things work under the hood with the common fork-join pool is that there's a pool of threads, which, as we'll see, is typically the number of cores on the platform minus 1. And I'll explain why it's minus 1. So if you had 4 cores, there'd be 3 threads in the common fork-join pool. And each of these things basically runs continuously, scanning for work to do. We're just going to care about how it works with parallel streams in this discussion. There's other things we could talk about and will talk about in other contexts, but today we're just going to talk about parallel streams. The goal of the common fork-join pool is to keep the worker threads and the cores that they run on as busy as possible. We want them to be doing work all the time. I mean, why not? They're paid to do work. That's what cores do. Each worker thread has something called a double-ended queue, known as a deck, that serves as a worker thread's main source of tasks. So you can see here we have this deck, which is called a work queue, and there's 2 ends to it. There's this end, which is the head end, and this end that's the tail end, and we'll see that things happen in interesting ways in both the head and the tail in the deck that a worker thread manages. You can read more about a deck or a double-ended queue here at this link. I think it's pretty obvious what it does, though. A double-ended queue allows you to insert and remove at the head and insert and remove at the tail efficiently. The parallel streams framework will automatically create fork-join tasks using the splitterators we've talked about that are then going to be run by worker threads in the common fork-join pool. So as things are split, they're then handed off to those worker threads to be run. This is the way that works. There's a superclass that's part of the streams framework called abstract task. And if you go and you take a look, either this is the Java 8 implementation or any source code implementation, you'll find Java, util, stream, abstract task.java. And here's a piece of the code that is shown there. Of course, because it's Java source code, they don't have many comments here. I don't know why, but I will show you what it does. So the abstract task is responsible for managing the splitting logic, tracking of child tasks, and any intermediate results needed in order to process elements of a stream. And the key method in the abstract task, like any task in the fork-join pool framework, is the compute method. And the compute is basically what decides whether to split a task up into subtasks, into smaller chunks, and or to compute the contents directly. And as you recall, it decides to do it directly when it's below or at a certain size, and it decides to split when it's bigger than that size. So that's what compute does. And what it does, as you can see here, is it basically has this splitterator. We have this splitterator called RS, which is right side. And then we have another splitterator called LS. You can probably figure out what that is. That's left side. Remember, when you split something, you get a left side and a right side. And it goes into a while loop, basically taking the original source of the input, which is the original splitterator, splitterating for the whole data source. And it keeps calling try split until try split returns null. So if you remember when we talked about try split, I told you how try split worked. If it got to a point where it didn't want to do any more splitting, it returned null. And if it wanted to split some more, it would return non-null. Well, that's exactly what's going on here. So we're calling try split, and we're getting back a left-hand side. The right-hand side has just updated itself because that's what try split does. And as long as it hasn't reached null, we're going to do some stuff in this loop. And what we're going to do here is we're going to keep track of whether we forked the right-hand side or we forked the left-hand side the last time. And as you can see in the comment, it says we're going to alternate which child is forked to avoid biased splitterators. So if things don't split evenly, we don't want to always fork on the left side because we'll end up with like a linear linked list of splits. We want to try to balance things out as much as we can. That's sort of an implementation detail just to try to be clever. But you can see every time you fork right, you change that to false. And every time you didn't fork right, you change it to true. Whenever we decide what we're going to fork, and you can see what happens here if you decide whatever you decide to do, you set this task to fork to either the right child or the left child. So now we have a task to fork, and we fork it. So remember what fork does is it arranges to run that subtask by putting it in the deck of the calling thread. That's the key thing to remember. When you fork something, whatever thread you're forking in, it will go ahead and take that task and push it on the head of the deck. And we'll talk a bit more about that in a second. And then, this thing will just go back to continuing to split. So we're basically forking. And by default, you always start out on the thread that's doing the forking. But because of the magic of work stealing, as things get stuck on that deck, obviously the thread that's forking isn't able to process that stuff. And there could be other threads that are sitting around going, I'm bored, I have nothing to do. And when a thread is bored and has nothing to do, it goes and looks for other decks and other threads that are busy to steal work from the end of the queue. So that's what's going to happen for threads that are not doing anything. They're just waiting to steal work from some other deck where the thread is too busy to get all the work done. After try split finally returns null, then it's going to do the leaf processing, and that will call this thing called for each remaining, which will then process all the elements by calling their try advance method on the splitterator. So it'll call try advance to work through that stuff. So that's the part after we've forked. When we get back a null, then we'd go ahead and process what's resulting sequentially by try advance. So as you can see, as I mentioned before, whenever fork is called in that loop we just looked at, that causes the subtask, the task to fork, to be pushed onto the head of the current worker thread's deck. So it always starts out by putting it on the current worker thread's deck, and that could happen, as we just saw, multiple times. Each worker thread, when it finally gets done forking, will then start to process the task or the subtask in its deck in LIFO order. LIFO, of course, being last in, first out. We all know what a last in, first out looks like. It's like a stack of trays in a cafeteria where you basically put something on the top, and then the next item that's taken is the one that was on top. So it's last in, first out. And there's a reason for doing that. We'll talk about that in a second. When a task is popped from the head of a deck, the worker thread will then run that task to completion. It'll do whatever that task wants to be done, and it'll do it until it's finished. Or, it could get suspended temporarily by the Java thread scheduler if there's more threads than there are cores, but the point is it'll run to completion. Why is it using last in, first out as the queuing discipline here? That's in order to improve locality of reference and improve the performance of caches. This is really important. So the basic idea, there's a pattern called fresh work before stale. And this is basically the fresh work before stale pattern. So by popping the item that was most recently pushed, you are more likely to have the data and code associated with that object in the processor cache, because you just put it there. You just did something with it, and now you put it in the front of the stack, the top of the stack. You push it on the top of the stack. So if you pop it off, it's probably ready to go. Whereas in contrast, if you were to go get the one that had been there the longest, it probably would have been moved out of the cache, assuming it couldn't all fit in the cache. Modern caches are pretty big, but if you wanted to make a choice, you would prefer to go with the one that was freshest, because most likely it's been the one that has everything in its cache. So locality of reference, cache performance, these are physical dimensions of performance that matter, and therefore they optimize it by using LIFO. Okay, so that's what happens from a point of view of any given worker thread in its deck. It tries to get things out of its deck. What happens when it no longer has anything in its deck? What happens when it's not playing with a full deck? Sorry, bad pun. So when it doesn't have anything in the deck at all, what it's going to do is it will look around randomly, find another thread, another worker thread's deck, and try to steal task or subtask from the end of that other queue's deck. And it does it by stealing from the tail, and we'll talk about why it steals from the tail. So assuming for sake of argument that this worker thread has nothing in its work queue after it finishes processing whatever it popped off, rather than just going to sleep, it's going to go over and find some other work queue, let's say this one here on the left, and it's going to say, hey, you've got some work. I'm going to steal your work, and I'm going to steal your work from the end of the queue, the tail of the queue. Whoops. And why does it steal from the tail of the queue? Well, the reason it steals from the tail of the queue is because the way that the decks are implemented, they have different locks at the head and at the tail. So they have two different locks. There's a lock that manages access to the tail. There's a lock that manages access to the head. And as long as there's at least one element in the queue, in the deck, then if you go steal from the end, you won't be contending or interfering with any locking that's taking place at the head. So it's going to be more efficient. Of course, if there was only one lock, then we would have contention all the time. But they're much more clever than that. They have this double-ended queue with different locks, different synchronizers at the tail and at the head, and therefore we steal from the end. And another reason we steal from the end is if you think about the way that splitting works, we start by taking the entire data source, and we then split it, and we put that on, and then we take what's there and we split that. So if you split using that model, using the push model we were talking about, the LIFO model, the stuff at the end of the deck will be the bigger partitions, and the stuff at the front of the deck will be the smaller ones. So by stealing from the end of the deck, we're going to start with bigger elements, which we ourselves will then split. So you always want to try to split things that are big because you get a bigger bang for your buck by splitting big things in other threads of control. So that's kind of an overview of how work stealing behaves and how splitting works in the common fork-join pool, or fork-join pool in general, but we're focusing on the common fork-join pool because that's what the Java Parallel Streams framework uses. And again, if you take the sibling class this spring, I'll go into a lot more detail. You get a chance to play around with this. You'll see the pros and cons of different approaches. But this is good enough for understanding how things work internally in Java Parallel Streams.